Hey guys, this is our first video dealing with topic part 5, nuclear physics. So I'm calling this topic 1, where we're going to look at what's inside the nucleus and how to calculate something called the binding energy. So I just want to remind you, if you go to our course page, you can find the PowerPoints that I'm going to be going over right here. You see the relativity ones, and then here's the one I'm going to go over right now, nuclear physics topic 1, the nucleus. So you can download the PowerPoint and look at it. I've already done that, so I'm going to go ahead and do a slideshow so we can click through some of these things. All right, so first of all, what's inside the nucleus? You guys probably know this already. We have protons and neutrons. We call either the proton or the neutron a nucleon. So in terms of some symbols that we use, conventional symbols, Z is the number of protons. That's also called the atomic number. You might remember that from chemistry. Capital N is the neutron number, which is the number of neutrons. And then the mass number is abbreviated usually by A. I don't know why. But that is just the sum of the protons and neutrons, or the number of nucleons. Okay, so how do we represent a nucleus? Conventional way to do it is you would use the chemical symbol of the element. So I'm just using a generic X, but this would be the actual chemical symbol. And then on the left here, a subscript, you have the atomic number, the number of protons, and then up here on the left superscript, you have the total number of protons and neutrons, or the mass number. Another way you'll see this written is you'll see the symbol dash and then the mass number. So for example, you could have carbon 12. That would be read as carbon 12. The way you could represent that is with the chemical symbol C. You see down here we have the atomic number 6, and then up here the mass number, or you'll see that written as C-12. So how many protons does carbon 12 have, and how many neutrons does it have? It has 6 protons, and then the difference between the mass number and the atomic number is the number of neutrons. So carbon 12 has 6 protons, 6 neutrons. What about plutonium-239? Right, so how many protons does plutonium-239 have, and then how many neutrons? So it'll have what? 93 protons, the atomic number, and then the difference between 239 and 93, that's the number of neutrons, 146. Or if I show you something like this, right, where the green circles represent protons and the gray circles represent neutrons, if you count, there are 4 protons and 5 neutrons. So 4 protons, that's going to identify the atomic species. And if you look up at in a periodic table, you'll see that that's beryllium. So that's going to be beryllium, right, with 5 neutrons. So the mass number is going to be 9, so that would be beryllium-9. You could represent it like this, the chemical symbol Be, 4 protons, and then a total of 9 nucleons. Okay, isotopes. So what is an isotope? Isotopes, they have the same atomic number, same number of protons, but different numbers of neutrons. So that means a different mass number. And every atomic species that we know of has more than one isotope, even little old hydrogen. There are sort of 3 common isotopes of hydrogen. We'll look at those when we look at this isotope data table in just a sec. But as an example, here are some isotopes of carbon. So you can see, right, all of these carbon nuclei have 6 protons, but they're going to have different numbers of neutrons. So carbon 11 has 5 neutrons, carbon 12, 6, carbon 13, 7, carbon 14, 8. There is this isotope data. It's an abbreviated table, and I'll show you where it is. If you click this link in the PowerPoint, you'll go there. But let me just end this show. If you go to our course page, okay, again, down at the bottom, I'm going to put this at the below our nuclear physics PowerPoint presentations. First, you'll see a periodic table. That's just a link to a periodic table, but you can find a periodic table online anywhere. What I'm looking at is this data right here. Okay, so if you click on it, now I know it's not terrific, okay, and it's not going to look great in the video. I just photo scanned these in from a textbook, but I like this table. It does not have every single isotope, but we're going to use this a lot, particularly because you have the atomic number, so the elements are listed in increasing atomic number. You have their symbols. You have the mass number, right? So these are going to be the different isotopes. So for instance, if you look at carbon right here, let me make this a little bit bigger. Okay, so if you look at carbon right here, you can see that it has carbon 11, carbon 12, carbon 13, carbon 14 isotopes listed. The other thing that we're going to use it for is the atomic mass. We'll say more about that in a bit. And then also when we get to radioactivity, we're going to use these last two columns. So get used to going to this particular abbreviated table from a textbook that we're going to use a lot. Okay, let's go back to the PowerPoint. And let me go screen presentation mode here. The charge of the nucleus, right? That's going to be determined by the number of protons. So you just take the atomic number, the number of protons, multiplied by the fundamental charge. Oh, I should mention, if I go back a slide, these are common abbreviations for the nucleons. P with a little plus subscript, just indicating, right, that the proton is positively charged, and then the neutron N with the 0, emphasizing that it's neutral. It doesn't have an electric charge. And then E, right, if you're talking about the electron, that would be E with a minus superscript, like we've used in class before. Okay, so that's the charge of the nucleus. The next thing is the mass. Okay, so as you can imagine, the kilogram is just way too big to be used a lot. So the common unit that we use is called the unified mass unit. You use this probably in chemistry. You may have called it the atomic mass unit. That's the same thing. The abbreviation for the unified mass unit is U. The atomic mass unit is AMU. I use unified mass units because it's less to write. Officially, this is given the name of a Dalton, but I don't know. I think everybody still just uses U. It's defined on the mass of a neutral ground state carbon-12 atom. So by definition, a carbon-12 atom with all its electrons in the ground state has exactly 12 unified mass units. Now here's a handy conversion factor that we're going to use a lot. One unified mass unit, it's equal to this number of kilograms, but yeah, that's nice, but that's not the one we're going to use. We're going to use this fact. If we express the mass in MeV per c squared units, one unified mass unit is 931.5 MeV per c squared. You'll see how we use this conversion over and over and over again. Okay. Oh yeah, the isotope data table that I was looking at before, it has atomic mass units. So if I go back to the table, this column right here, it has atomic mass units. Now the fact that these are masses of the neutral atoms and not the nuclei, we'll have to keep that in mind, especially when we look at radioactivity, when we're doing some calculations there. Okay? Okay, so let's go back to the PowerPoint and let's see. I think the next topic, is the radius. Okay, yeah, here's an equation. It's not that important, but it does give you the sense of a nuclear dimensions. So roughly the radius of a nucleus, if you consider it a sphere, is some base radius, R0, which is 1.2 times 10 to the minus 15 meters. 10 to the minus 15, that's femto, so that's 1.2 femtometers, FM. But the radius goes as that base radius times the mass number to the 1/3 power, roughly. Okay, if you're going to view the nucleus as a sphere, which in some cases it isn't even a good thing to do. But there's a formula for you. I don't really use that very much, but there it is. The strong nuclear force. You should know that what holds the nucleus together is one of the 4 fundamental forces that we say in our model of nature. So it's called the strong nuclear force, to be contrasted to the weak nuclear force that we'll talk about later when we talk about radiation. The strong nuclear force has some very distinct characteristics. First, it is an attractive force between all nucleons. So neutron attracts neutron, neutron attracts proton, proton attracts proton if they get close enough. It is extremely short range. That brings us to the next characteristic, extremely short range. So it's only going to be strong over a few femtometers. Once you get beyond that, then the force falls off dramatically. And it is extremely strong because if you think about it, right, that Coulomb, the electric repulsion of the protons, has to be overcome. In fact, that proton-proton repulsion is a key fact in determining nuclear stability, as we'll see later when we talk about radiation. Okay, there's one calculation that I want you guys to be able to do, and that's to find what we call the binding energy of the nucleus, E sub B. You can think of this as if you wanted to break apart a nucleus into its individual neutrons and protons, how much energy would you have to put in to do that? Now, an amazing result is if you add up the mass of the individual free nucleons, right? So if you take, let's say your nucleus is boron and has 5 protons. So take the mass of 5 isolated protons, and let's say it's boron 11, so it has 6 neutrons. Take the mass of 6 isolated free neutrons. If you add up the proton and neutron masses, you will actually get more mass than if you take the mass of the bound nucleus, those 11 nucleons bound together. And this is where Einstein's special relativity theory was so critical in understanding this. Some of the mass of the isolated free nucleons is actually converted to energy. So to find the binding energy, you have to first calculate what's called the mass deficit, delta M. Once you have that, you multiply by c squared, as Einstein tells us, and you will get the binding energy. So how do you find the mass deficit? Okay, you take the number of protons, and we're going to multiply by the mass of a hydrogen 1 atom. Because we have to use atomic masses, hydrogen 1 is just a proton, right? So we're going to take the mass of a hydrogen 1 atom, multiply by the number of protons, plus we're going to take the number of neutrons, which is the mass number minus the atomic number, times the mass of an isolated neutron. We'll add those together, then we'll subtract off the mass of the bound atom. See, that's why we have to use hydrogen 1 atomic mass here, because we're going to be using the mass of the bound atom here. Okay, so as an example, watch, we'll do an example. Let's suppose you want to find the binding energy of a carbon-14 nucleus, and then we'll divide by the number of nucleons to get what's called the binding energy per nucleon. Okay, so what I would have to do is I first have to find the number of protons. So how many protons does carbon have? Look, I can go to, let me end that show. We'll go to that table. I look for carbon. There it is right there. It's 6 protons. Okay, so when I go back here, I'm going to take 6 times the mass of hydrogen 1. Okay, I've got to go back to my table. Hydrogen 1 is right here, 1.007825. That number is going to be used all the time when we're doing the binding energy calculation. Okay, so if I go back here, you can see I have 6, right, times that mass. Then I have the number of neutrons. That's going to be 14 minus 6. That's 8 times the mass of a neutron. Now, if you go back to our table, the first mass listed is the mass of a neutron. They put it in parentheses because it's not an atom. But that mass is also going to be used over and over and over again, the 1.008665. Okay, so you see that right here. There's that multiplication. Then I have to subtract off the mass of the bound atom. So I need the carbon-14 atom mass. So I go back to my table. I find carbon. I look for mass number 14, and there it is right there. Whoops, right there. 14.003242. So you see that right here. I end up with, and these are all unified mass units, I end up with delta M, the mass deficit, in U. Now watch this. To get the energy, I multiply by c squared, but I'm going to use this handy-dandy conversion factor. So I take my mass in U, no need to convert to kilograms. We're multiplying by c squared, but now I multiply by my conversion factor. There's 931.5 MeV per c squared in 1 U. So the c squareds cancel, the u's cancel, boom. Just multiply your mass deficit in U by 931.5. You're going to have the energy in MeV. So there it is right there. And then if I divide by the number of nucleons by 14, I get what's called the binding energy per nucleon. So they sort of share that binding energy, right? So 105.28 MeV to break this nucleus up, and that's about 7.52 MeV per nucleon. You can do the same thing if you want to try it for helium-4. A helium-4 nucleus is actually what we now know, right, to be an alpha particle. So when alpha particles were discovered by accident with these heavy nuclei spitting out these alpha particles, people didn't know exactly what they were. They knew that they were pretty big and positively charged. Well, now we know that's a helium-4 nucleus, which, if you think about it, right, helium-4, helium is 2 protons, so helium-4, that's 2 protons, 2 neutrons. So you can do a similar calculation for the binding energy of helium-4. I've got the number of protons right here, 2 times, look, the mass of hydrogen-1. That's always going to be right there in your binding energy calculation, the mass of hydrogen-1. The number of neutrons, in this case 2, 4 minus 2, that's always going to multiply the same number, the mass of the neutron. What changes is this number right here, right? Now we want the mass of the atom of helium-4, so I looked up the mass of helium-4 right there. I put it in right there. I get a mass deficit of 0.030377 U. I multiply by c squared and my handy conversion factor, and boom, I've got my binding energy, 28.2962 MeV, to break up an alpha particle. If I divide by 4, I get the binding energy per nucleon. And this is interesting. Even though helium-4 is a tiny little nucleus, it's actually really tightly bound together. See, that's 7.07 MeV per nucleon. That's close to the binding energy per nucleon of a bigger nucleus, a carbon-14. Alpha particle is an extremely tightly bound particle, it turns out, which is why the big nuclei, we'll look at those later when we talk about radioactivity, the big nuclei will spit out alpha particles because they're so tightly bound. All right, I got to end right now. I'll be talking more about stuff in the next videos. Bye.